Welcome back, everyone. I don't know about you. Yesterday, I started my day at 5:30 a.m. It ended at 1:30 a.m. We had a hackathon yesterday, and I just wanted to let everyone know what the results of that hackathon was. So, if you go to RavenDB, to the RavenDB repository, ayenda/RavenDB, there is a new branch. It's called the docu branch. And in that branch, we have a new feature, counters, and you can select the relevant counters. Now, what we have managed to implement so far is actual storage, actual web endpoints. For doing that, we implemented, obviously, the UI, not final, send bugs to Judah, and we're still waiting for a replication from Kijana, which hopefully will be today. But this is just to give you some idea about what we want and where we want to get it. Because we were able to sit down at dinner yesterday and talk about the design and split to several teams and then do everything in a space of, what was it? 4 hours, maybe less. And then I had to spend some time integrating everything because we work on separate and absolutely disconnected teams, but that worked. So this ties very, very well to today's talk, because today's talk I'm going to show you something that's either going to be awesome success or an awesome fail. Just to make things interesting, I did not practice this talk. So here's the deal. Remember that I told you that Voron is a game changer for us? And the reason that Voron is a game changer for us is because it does to the storage solution what RavenDB does for line of business applications. Basically, it makes it trivially easy and simple to start building any sort of low-level storage solutions. Something that I would have to go with ESENT. Doing something with ESENT takes about 3 hours just to get the environment right. Doing something with Voron is like this. So this is what we want to do. We have heart rate monitor watch. And that's pretty simple, right? Every 30 minutes, it sends an update to a remote server, and it says, this is my watch ID, this is the current time, and this is the heart rate that we have. And we sold 100,000 of those. Now, so far, everyone is good. We have this, apparently this guy is about to die, according to his heart rate. But we have these watches, we sell them to them, and then we realize something very, very nasty happened. People actually want to use them. And what do you think people want from this type of information? They want pretty graphs. They want to be able to see what have we been doing, where have we been doing that maybe, all sorts of stuff like that. Show me my heart rate over time, show me my heart rate by hour over time, etc. We don't care about all of that. We care specifically about this information because we need to store and query that in an efficient manner. So this is called a time series database. Why is that? Because most of our data is time and value. This represents some very interesting implication. To start with, we only have a ping every 30 seconds. Ping every 30 seconds is very, very low rate. It means less than 3,000 events per day. About 1 million after a year. Who cares about that? The key point is that we sold 100,000 of them. And that means that after a year, we have 100 billion. So this is what we're going to build today. A database that can handle 100 billion records in about 45 minutes. Just to give you some idea, that also means that we need to have 35,000 writes per second sustained. Okay? So how do we do that? And that does mean user want to solicit opinion from you. How are we going to handle this? How would you approach doing something like that? Anyone think that they can just pull out SQL Server and start working? Seriously? Anyone? Why not?
Inserts suck.
No, actually no. Insert in a relational database are very, very fast. The problem with doing this sort of thing is that over time you're going to get into a lot of values, and you have to be very careful about how you insert, how you run. More specifically, doing 3,500 inserts per second is not trivial, especially because at the same time, you want to run a lot of aggregation queries. Give me all of the values for a specific watch in a specific time frame and group it by day, for example. That's really expensive to do. So we are not going to be able to do that. We're also not going to be able to do that in RavenDB. Why not? By the way, both RavenDB and SQL Server can actually handle 3,500 writes per second. The problem is, what do you do with the information afterward? And you had an answer for me?
No. You said you're going to have RavenDB and SQL Server that can come out, but because of probably the login on there.
No, they can. They can handle that. The problem is, what are you going to do with that afterward? In the case of RavenDB, you have very, very, very small documents. So, 2, 3 properties, and you're not doing much with that. So, yeah.
Well, I'm sure you're going in a different direction, but what I would probably do is try to think about how to create predefined buckets for hour or per day to throw those counters into so that I can increment a value and have meaningful data in the database instead of every single little individual.
Okay. You need heart rate information. That's the reason that I chose this example, because it's really hard to want to say, oh, I will just give you your average heart rate. It's meaningless because you went to the gym you ran for half an hour, and then you went to the sauna. What's your heart rate during the gym? Okay. So what we're actually going to do, we're going to have the following design. Every watch has an ID. I chose 40 characters because GUIDs are 36, and most industry standard serial numbers are way below that. And the interesting thing is that we model every watch as a tree. Now remember, in Voron, every tree takes a minimum of 4K. Yesterday, with the counter example, we actually started modeling things with every counter is a tree, but we realized that it would be horrendously expensive in terms of disk space, because a counter usually should take 192 bytes. But if we put it in a tree, it takes 4 kilobytes, so that's a lot of wasted space. So we changed that. But so we use a tree per watch. The next thing that we do, and remember, a tree is just a key and a value. So the value is big endian date. Now, do you know what big endian and little endian is? Anyone? Yes, the order of the most significant bytes, which is probably the least interesting thing you could ever think about. So this is, by the way, do you know why they are called little endian and big endians? Do you remember the Gulliver Travels book? Do you remember the Gulliver Travels book? They have a with the Lilliputian wars. They started because some people wanted to start eating the egg from the small end and some from the big end. So they had the little Indian party and the big Indian party and social commentary for the 19th century. So anyway, so we want to do it like this. We want to use big endian. This is something that you do a lot with Voron because Voron uses key that are byte strings and just compare them. So you want the most significant part to be on the left, basically. So it is compared naturally when we have higher values. And we have the heart rate number as a value. We're just going to use that as a double. As a result, every entry per watch is going to cost us about 16 bytes. It's not really true. There is some overhead, so it's going to cost us about 20 bytes. Okay, so the basic idea is that I really want someone to time me. And let's go and start. I set up already a project, and the project has Voron in it, and the project has just a tryout so we can try. So we're going to start by creating a new class and call it time series storage. It's going to be disposable. And we're going to take the environment options as a parameter. That means that I don't have to worry about who is using my system, what is my pet, something like that. Whoever calls me is going to be responsible for that. And now we need to initialize things. So we are starting a write transaction. And we want to have some information about what's going on. So we usually go with a metadata tree. I find that doing something like this is very, very helpful. So this is literally just, we are now in a new DB. So the ID is a new GUID. Result reader read byte 16. Okay, this is everything that I need to do. Just a metadata tree that for now it's only stored the ID of the database. I like to have a GUID ID for databases because it helps if you have to deal with replication or stuff like that. Most of the time, we don't really want to expose that to the user, but it's helpful if we need to figure out on what system was this written to. Now, it's important to understand that when I'm writing, I want to have the idea of batches. So I'm actually going to have this style. And this is now time series storage. And storage storage environment, new transaction. So for now, we do it like this. Notice that we use a write transaction because only a single thread can use a write transaction. We know that inside the writer, we don't have to worry about thread safety. So what do we need to do now? We need to actually do the write. So the basic idea is that we have watch ID and just this. Okay? And what we're going to do now is say this. Now, get tree in a write transaction has the side effect of creating the tree if it doesn't exist. So now time x. So I'm taking the ticks value because that is that is a very simple number of ticks since epoch, and I'm converting that into a big endian byte array. And now I can do this. Just like that, and now only thing that I have left is key. And now this is done. Now I'm going to go here . Now we're pretty good. Let's see if we can write this. For now, I'm saying just run in memory. Don't care about files. Now, one, two, three. Let's not kill this guy. And one thing that I forgot to do, we actually need to commit the transaction. That is because I need to switch to this guy. And still doesn't like me. Why? So we basically had to make sure that we're running on the 4.5. Okay. So now it's working, presumably. By the way, everything here is available on GitHub. You can go to the tempo repository on AND. And everything will be available after the talk. So now we have writing. That's great. By the way, you may not have noticed, but I did something very interesting here. I support the notion of batching. And how do I do that? When we have a writer, everything inside this writer happen in a single transaction. So those two would be written at the same time. What's my next step? People? Okay, so how do I get the data back? What sort of API do I want to have? Okay, so let's try doing something like this. We already have the concept of create writer, so I'm going to use the same for creating reader. Notice that now I'm creating a read transaction. The nice thing about read transactions is that you can have as many of them as you want. And they don't stop they don't stop you from doing writes. So now we want to do So now we want to do something like this. We always have query by the watch ID. If I want to see my heart rate, I don't care about your heart rate. And if I want to see aggregation over the heart rates, that's something that I will do that's something I will show you how to do in a bit. And now we just say datetime from datetime start to. Okay. By the way, I'm equal. We are now in a read transaction. If I'm trying to access a tree that does not exist, I'm going to have an exception thrown. Now, remember that in Voron, trees are just sorted B trees. That means that I can iterate over them. And that's important because I can do this. Start buffer. Now it dot sick. Okay, so what I'm saying, and because those are such common things, we actually made them explicit in the API. We have a max key. So I want to iterate up to that point and go to the first item on the tree that equal or greater than the start value. Again, notice that we use big endian convention because that gives us the most significant bit. That means that we can compare using a memcompare, and that's about it. Now we are iterating over the tree. And now, what I want to do is just get the data out. And it creates reader, yield return, and datetime from because that obviously makes a lot of sense. There is a small inconsistency here. Please ignore that I'm doing that. When we're reading from a value in here, we're using little endian semantics. And I'm not going to do that. I'm going to do that properly. And okay, so now so now we have the value, and now all I need to do is encode in a big in 64. What the hell? And now I think I'm done. Everything compiled, so we can go home. Let's see if this actually works. It would help if we actually could get a reader. And for each r dot query on 1, 2, 3, 4 from datetime now add days -1, datetime now add minutes, yay. So the problem is that ticks must be between min value and max value. Usually that's an indication that I'm switching the endianness. And yeah, that would help if I wasn't being stupid. I don't even need that. So the problem here is that I was trying to read everything from the value, but we didn't set it up like that. We have the key and the value. So we need to read from the value 8 bytes, and those 8 bytes go indeed into the value. But from the key, this is where we actually put the actual value. So this is where we put the actual tick for this entry. So look at this here. What is the key here? The key here is the tick's value. And the value here is the double value that we have here. So here we are getting the ticks from the current key and reading the actual double value from the value. And that's lovely. Yes, yes, of course. Wait. So how much time? 19 minutes, okay? And we have a time series database. Now, here's a question. How fast can we push data in? Anyone wants to take a guess? I have absolutely no idea. But here's what I'm going to do. No, I'm going to do it like this. Stopwatch. So let's run for 10 seconds. And let's add 100 values. Per commit. And we're going to do that on five watches. And so like this, a double. It's not a very meaningful thing, but okay, and good enough. And what I want to see now is amount of time that it actually took, number of items that we push into this, and count slash So if I did everything right, this is supposed to run for about 10 minutes, sorry, 10 seconds. And after 10 seconds, it's going to give us some numbers. Okay, so within 10 seconds, we added 5.7 million records at the rate of, oh, you can't see that. Second.
It's just that one screen.
Okay, so 5.7 million at a rate of 570 entries per millisecond. And I cheated. Where are we writing this to? Did anyone notice? We're writing that to memory. So effectively, we're testing stupid stuff. But it makes for a very impressive demo, you have to admit. So now we're going to have to go to the trouble of actually running that against a real live system. Now, this is about 1.5 years old. It's an i7 with an SSD. And let's see what happens now. So before we review, any guesses about what the performance is going to be like? I would be shocked, I tell you, if this is going to be more. Give me numbers. Let's do the easy numbers. 570 per milliseconds in memory. How much do we expect to do? How much do we expect to do with disk? Yes. 5%. And in numbers, how much that is? 25 per millisecond. Do you see the numbers? For fun, this is 4.5 million records in 10 seconds. This is 450 per millisecond. Remember that a rate was required for 3,500 per second. Again, I'm cheating a lot. For one thing, we are actually using a very small data set, so it's very easy for us to get very high numbers. But the interesting thing here is that, look, we added, let me give you something even more interesting. So now what I want to do, I want to also see the count of transactions that we have. And the reason that I'm saying that I'm cheating here is that what I've actually done is, okay, you see? The actual count of transaction is drastically lower. I don't know what, I have no idea why there is such a big difference, but the count of transaction is very much, oh yeah, of course. By the way, we're still writing to the same files. So we can go here and actually look at what Voron has done. And you can see that we have written about half a gigabyte. And this is the actual data file, and you see all of the journal files. By the way, you can see that we started with very small journal files, and we increased the size to match what we needed. And we're going to run it again. And while we are doing that and while it's doing stuff, notice why I say they cheated. Because I'm not able to do that many transactions per second. What I am able to do is do this. Which means that for every transaction, I'm shoving 500 items to the database. And why are transactions so expensive? Sorry?
F-sync, right?
Yes, we are not actually using F-sync, but yeah.
Okay, files.
Yeah. So By the way, notice that the number of journal files have gone down. I'm going to switch it up to, let's say, run for a minute, no, for 1 minute. That's 60 seconds, Oren. And we're going to see what's going on. So a few things to notice. You can see that we have the journals. And as time goes by, we add additional journals because we keep writing. You can see that we have the actual Raven Voron. And the Raven Voron is the actual data file. For fun, the Voron means Raven in Russian. This is actually Raven. You can see that we have the scratch buffer. This is what we talked about yesterday, the temp stuff. And you can see that right now we're holding about 400 megabytes in the scratch buffer. The idea here is that we save a lot by just being able to run through everything. Notice that we have we had a compression buffer here somewhere. What happened to those? Oh yeah, we shut down. When we shut down, those items were deleted. Let me try running this again so I can speak about this. Oh wait. So here we go. So look at the scratch buffer. This is where we are actually storing the modified data that we write to the journal. Write to the journal, everyone is happy. The key part here is that we don't have to flash it to the data file all that often. That's why I said that it's very nice to be able, you saw that the data file was just updated and some journal file would be deleted shortly. Notice that if you look here, you see that the compression buffer, this is the max size of any transaction that we have ever had. Because this is the file size that we use for transactions. For compressing the transaction down so we can write it to the log. So effectively, every transaction that we have is about half a meg. And we now have a database that's about 3 gigabytes in size. And you can see how that works. So it looks like when we stop cheating, you probably can see that. When we stop cheating and actually look on real data set sizes, and I think that we have, hundreds of millions in here by now. So we can do about 250 writes per millisecond. And this is sustained, as you can see, because we run it for a minute. Real life work would actually require us to do that for longer than that. Now, let's see a worst case scenario. What's the worst case scenario that we could have? One transaction, one write. And now I want to make it just 5 seconds. We will still use, sorry. Now we're running for 5 seconds? Yes, 5 seconds. And now we are down all the way to 4 writes per millisecond. Now, interestingly enough, that is on a relatively large database. We're now at the multi-gigabyte range. That's still significantly more than we can have, than our requirement of 3,500 per second. So with this guy, we can do 4,700. Again, this is a laptop. We haven't done the optimization for spreading it out on multiple disks, but it's working. Now, I want to do something else. We've written a lot of data into the database. I want to now check read speeds. And I'm just going to commit that. And we don't care about this now. What I actually want to do is something quite simple. I know that there is a reader equal TSS create reader. And what do I want to do? Let's just read everything and sum up the value. So 5. So this is actually go read all of the items that you have. I actually do not want to do that like this. Sum plus equal heartbeat. Count plus plus. Yeah. Now I want to see how long it took you in milliseconds. How many items did you read? Just for fun, what was the sum? So this is going to take a while. Notice that we now have 3 gigabytes of this data, and we started from scratch. Oh, wait. So this is the worst case scenario for reads. Why is that? It's the worst case scenario for reads because we started from a cold boot. We just started the application. There are no caching involved. There is nothing else. But in just over 5 seconds, we're able to read close to 10 million records and do something with that. So given that probably you aren't going to need to query all 10 million records all at once, I'm pretty good with our performance so far. Because from my perspective, I don't have to do anything else, and I'm meeting the SLA that I initially specified. Questions so far? Yes?
Voron a product?
Yeah. Yes, we would sell people Voron. More interestingly, what we are interested in doing is you come to us and say, I have this specific need for persistence, and we provide you with a complete solution. The reason that I don't like talking about Voron as a product is that Voron is a storage solution. It's a very, very good storage solution, but that's where it ends. For example, you don't have UI. For example, you have to handle things like, sorry? No, no, we handle that. You have to handle things like, what's going on in my database? How do you handle moving between versions of the application? How do I move the data from one format to another? All sorts of stuff that you would have to deal with if you're writing your own database. We actually have a service. We actually had it for the past 2 years. We just never made it very public. That I need to store data in this shape, in this format. Come and help me do that, and we provide you with a complete solution from the UI to the how you handle incremental backups to how you handle replication, that sort of thing. Okay. Before we open the floor to a lot of questions, and I think that I'm again rushing things because I thought it would take me more time. I really like this. Here's a problem. Okay, so those are the sort of things that we did. We already did that. Everyone is happy. Here's a problem. The current code base makes sad assumption. Only one writer at a time. That means that we really can't scale very well for multi-threaded applications, right? What do you think? Can we or cannot? Can we scale for multi-threaded? Sorry? You could use a queue, but let's do the stupid thing first, okay? Let's just write a bunch of threads and see what happens. So I actually have a free space issue here, so I'm just going to delete that. And where is that? Doing reads. So now, what I'm going to do, I want to write, again, for 10 milliseconds, for 10 seconds. Task. So, and now let's just do, and again, we're trying to simulate the absolute worst case scenario for us. A bunch of writers that all write each of them write their own thing. Remind me to talk about what happened for concurrent modification to the same value. And we don't care about that. Let's see how much we're able to write here. Anyone want to take a guess? Previously, in the single-threaded mode? Okay, So we were actually able to write 42,000, which comes to about 4,200 per second. And that's nice. That's several percent point lower than before. And the reason that this is so, this happens is that we're actually able to prioritize things. We're able to take the log for very short amount of time, so there isn't a lot of logging. But as it stands, the current API does not lend itself well for concurrency. If we had longer tasks inside the writer, that would take us a lot longer to process. So what we're going to do now, we're going to try to make it more multi-threaded friendly. We're going to do that by not holding a lock. Instead, we're going to do something called Rightpatch. What the? Oh, wait. And now in the commit, what we're going to do is a storage environment, writer. Technically speaking, we didn't change much. And we kept the same semantics. Let's run this. And hopefully, if I did everything right, it's supposed to give us high rate of you see this number? I actually want to run this again because I can't process numbers like that. And again, now we're talking about a lot of activity on the database side. We have about half a gig, which is respectable. More, seriously? It just went away, sorry. More importantly, we're going to hopefully see something very interesting. Before, using multiple cores, I was able to do 42,000 per 10 seconds. Now I'm able to do close to 3 times that. Why is that happening? I didn't make a major change. What happened? Sorry? I also did it before. The changes that I made were very, very minor from the code perspective. Instead of having a transaction, I have a Rightpatch. Instead of getting to the tree and adding to that, I'm adding to the Rightpatch with the specific tree. And finally, I'm calling this guy, the writer write. So what's the change? What actually, sorry?
Putting multiple batches together to do something, right?
Exactly. So what happened is that I'm submitting this to the database to be written. This actually goes into an internal queue. There is a separate consumer that wakes up and say, you know what? Let me read from the queue. Oh, here is a batch. Here's another batch. Here's another batch. Let's take all of these batches and let's write them all in a single transaction. Remember how before we were able to do close to 600,000 per second because we were doing 500 writes per batch, per transaction? The expensive part from our perspective is the number of times we commit a transaction. When we do this, we don't commit a single transaction. We call write. We don't commit a single transaction. We commit multiple concurrent write batches. So we are actually able to scale very well with concurrency. Yes?
Is this ACID still?
Yes. So here is a fun fact. Well, no. It's AID. So it's atomic, it's isolated, and it's durable, but it's not consistent. And it's important to understand the major difference, because the answer is that yes, it's still ACID, it's just not in the same way that you think about it. So when you're writing a write transaction, in a write transaction, you own the world. People can look, no one else can touch. When using a write batch, you're saying, I want this to be written to the database. But between the time you say this and the time you actually write, it is possible for some other thread to go in and modify that value for you. In order to handle that, we have a nice overload here. That says, what should we do? And we can say, okay, I only want to update this value if it matches the version that I have. And this guy says, if it doesn't match the error that I have, just skip this value. It's not an error if it's already there. If it's set to, if it's by default, it would throw in concurrency exception and abort this transaction. So that's why I said that it's not as consistent as a write transaction, because you may have multiple writers working at the same time, and you have to take that into account.
Where's the durability here then? Like, where does it get written?
Here, after write exit, after write returns, it's on the disk. Before you call write, it's just inside this object. There's nothing else. Now, so this is concurrency. This is us getting very high rate of concurrency for writes. What I'm going to do now, I'm going to basically let it run for a while. Let's increase this to 30 seconds. That should give me enough time to do the alternative. Right. Yeah. So now we move to concurrent writes. Now I want to do concurrent reads. And basically what I want to do is let's do it like this. Reader query key min value, max value, count. So now a task wait all array. So now basically having 8 concurrent threads reading from the database. And what we want to do afterward is to say, well, how much time this took, and how many records did we read? Task of int. Okay. So that was it. So I don't think that we can actually use, let's try this one. So in under 200 milliseconds, we're able to read 700 items. And that's on a database whose size currently is, well, nothing. Let me just cheat. I want to show you what happens when we write lots and lots and lots of stuff. Thousand. That's a good one. No, because what I want to show you what happened when we crash. So I'm basically going to look here. I did commit, didn't I? Oh, yes, same value. So again, remind me to talk to you about this. Okay. Because what happened, and the reason that we didn't see a lot of growth, is that it kept changing the same thing. So it always modified the same value, so we ended up not changing a lot of stuff at all. So, by the way, look at, you can see that we have a lot of scratch memory, and we're starting to see relatively nice increase in size. Every transaction is about 8 megabytes at this point. And see. Now I'm just going to crash. Sorry?
Are you going to run all the way out of this space?
Yeah, we actually have specific handling to doing that. But if I wouldn't stop it, yeah, we would run till it runs out of this space. What I've done now, we have about 1 gigabyte. Now I'm going to start it again and see how fast we can read. Notice that what happens now is that we run recovery. We basically went over the entire database and saw how we can recover from the issues. And now we have 7 million records to read. We're able to do that in a single second. So the nice thing about Voron is that it plays very well with concurrency. And to remind you, this was a forced requirement. We have to do a 3,500 sustained writes per second. We got to half a million writes per second without even trying on a single core. And we saw that we can do 100,000 writes per second quite easily using concurrency, using the worst case scenario of one value per transaction. Okay, so we've done all of that. If we wanted to have a real-time serial server, we would probably need to have actual server to do that. And a lot of the effort actually goes into the wire protocol. A lot of the interesting issue comes with regards to how are you always going to keep all of the data? A lot of the questions come down to, are you always going to handle, are you going to consolidate it somehow? For heart rate, it isn't really meaningful, but there are many scenarios where it is meaningful to say, oh, I want to select just single value per day. This has been I don't know, can't think right now of any such scenario, but there are many such scenarios where this is meaningful, so there is also need to be handling for that, but this is not something that the storage care about. As far as I'm concerned, we were done with the storage after 20 minutes. Everything else was, let's just demo and test that, nothing else. Questions? Yes?
Can you set up a scenario where you're actually doing the read on the inserts at the same time? We have separate to
Yeah, sure.
have two different sessions running.
Uh,
Results from each.
I don't know how to do that. Give me a sec. Oh yeah, I know how to do it. What's wrong with you? So basically what we want to do let's say that we want to run it for 30 seconds. And here we have and that should be good enough. So what we're talking about is what happens when we have concurrent reads and writes. So this will take 30 seconds to answer. Note that at this time we are running both the reads and the writes at the same time. We're going to let 30 seconds elapse. Probably by this time, the reader are done. Something that is important to understand, a reader sees a snapshot of the database at the moment it was created. So even if I committed the transaction, if you have a reader that was open before I committed that transaction, it won't see my changes. It sees a full standalone snapshot. And to answer your question, we're able to write 4 million while we're reading 7 million. Okay? And the key point here is that we don't have any desire to try to handle, we don't have any issue with concurrent readers and writes. But I don't know if you noticed, but we are still using the Rightpatch method. So we can actually have concurrent writer, concurrent readers, and not worry about it. More questions? Oh yeah, so What happens if we have two values for the same date time? Well, in the case that we have here, we don't care. We just treat that as, oh, you're fixing an old value that was wrong. So we will overwrite that value. That's why before, when I had the datetime now, and we ran in a type loop, so it was the same value, nothing happened, because we kept just updating the same thing. So just a reminder that you have to consider what happened when you want to overwrite, especially with dates, and especially because then you have to consider what is the granularity of changes that you care about. Because in this case, we care about the granularity at the tick level. Usually you care about the granularity at the day, hour, or rarely you care about the granularity at the second level. So you have to consider how you handle that. More questions? That's it? Yeah. Can you explain what you mean?
Let's say that one car
Yes.
running on the car has lots of sensors pulling out tons of events. And you want to know over the last 4 laps what notification is.
We have actually done that when we are doing the reads. I don't know if you noticed. We did the sum of the value. So we aren't dealing with aggregation ourselves. We just give you the data. And I think we did something like millions per second or even more than that. And the nice thing about it is if you're compute bound, you can parallelize your effort because we will give you the data as fast as you can process it. Okay, so something that I've seen people do is, okay, we're going to say, take very low resolution data, and I'm going to get the speed of the car for every 10 milliseconds. And that's great, but I actually want to show a speed of the car per lap, the average speed of the car. So I'm going to store the high granularity data, then I'm compute and store the high granularity, and you usually do that in multiple trees. More questions? Yes?
Do you have any particular challenges when you were testing this?
Can't hear you?
Do you have any particular challenges when you were testing this in terms of integrating with Raven and shipping?
We spent the last, year doing just that. Yes, we had a lot of challenges. Specifically with regards to Raven, yes and no. A lot of the stuff, because we already had Raven, and because we meant to use Voron for RavenDB, we designed up front a lot of the things that, so that they will match what we are doing. For example, snapshot isolation. The transaction merging was a challenge for us because it requires to work quite differently internally than how we do that with ESENT. With ESENT, you submit the write immediately, and it immediately tells you, okay, not okay. With Voron, in order to have concurrency, we use a lot of Rightpatches, and you only know if there is a concurrency conflict when you commit a transaction. So that was interesting to look at. What else was there? There was a lot of small, tiny things, lots of bugs in Voron, interesting things that only happen. Pavel and Arik are in the end smiling because they had to deal with all of that. But he had a lot of very interesting edge cases, race conditions, those sort of things that we had to narrow down. What happened if you read, commit, read, flash, commit, start a new transaction, and somehow it's the exact right moment, the journal file is not there or something like that. So Voron is a major piece of work. Seriously, we've done, it's non-trivial because just B plus trees in general takes a while to get around. A lot of the complexity is in the optimization that we applied, the fact that we have the journal, the fact that we have the scratch page, the compression page, the fact that you can be running on data from all of them together, and we have to make sure that the page translation table always points to the right location and that sort of things. And if it doesn't do that, it creates very hard to debug scenarios. But in general, it's a really good fit. It was designed for that, so it's not a big surprise. More questions? Yes? Can you just raise your voice?
How would the demo change the watch providing you with complex data instead of just array all-around data?
The API that Voron exposes is this thing. So basically, the value is a stream. So if you want to store complex data, go right ahead, it's not a problem. By the way, just for fun, yeah, and it's very common to have a single logical value be in multiple trees for various reasons. It's also very common to have secondary indexes as other data. I can show you. Yes, we are doing that very frequently. So you can see what we did yesterday with the counter storage. It's a lot more involved. It has multiple trees and a lot more work. But it does things very nicely and relatively efficiently. I'm still not that happy about that. But one of the things that I noticed Voron did to me was a lot more emphasis on speed and, oh no, I don't like this code, it does tree allocation, we can do it in just one, and those sort of things. But that's my thing. One thing that I want you to notice is that, let's do the code metrics for this. So we have a database, at least according to Visual Studio, in 38 lines of code. In practice, including all of the nonsense like that, it's 133 lines of code to have a database that is capable of handling millions of records per second and an insane number of writes. One last question. Yes?
How does it compare to ESID with regards to configuration and recovery times, that type of thing?
So with regard to configuration, it doesn't have a lot of config options. That's all in the storage environment option. And that's mostly regarding how you want to handle this. So you have the max log file size, the size of indexes, you have some data here, or do you want incremental backup, those sort of things. But so there are some things that you can tweak. How often should we flash from the data file, from the scratch to the data file, those sort of things, but there isn't a lot of stuff. Very important for us is that Voron is machine independent. That means that you can take a Voron database written on Windows 8, take it to Windows 2003, and it would work. I think that it doesn't work on Windows 2008, but that's some bug that we had to deal with, specific service pack that we need to look at. But That's important because it means that a lot of the time, when you move database around, you have to, with instant, you have to defragment them. Basically, you have to rebuild all of the indexes. That relates to why and how instant handle internal indexes. And that relates to the collation factor and to the operating system and what patch version you have and all sorts of other crap like that. With Voron, we intentionally avoided all of that. All of the keys are always byte strings. All of the keys are always compared in the exact same team. So we basically use memcompare. With regard to recovery time after an error, the only thing that we have to do is scan through the journal and apply the changes. I don't know if you noticed, but we actually had several times cut off the server. And when we restart, we had to apply hundreds of megabytes of journal files. And we've also done a lot of work there to optimize this. So the current rate is something like, you should be able to do in the order of 200 to 300 journal, 200 to 300 megabyte of journal file on startup without even noticing. It should take half a second to a second just to go over that. The reason this is important is that, as you mentioned, you have a failed server, you want to bring it up, you want to do it as quickly as possible. And I said, yeah.
Follow-up question.
Yes.
Would you say these machine independent if you use RavenDB or 3.0?
Yes.
Okay.
Yes. Yeah.
So we have just discussed about indexing. So you said indexing can also store in the Voron. So
Yeah, that depends on what index you're talking about. Because there is the RavenDB index.
yeah, but not RavenDB.
No, no, that's something entirely different. I mentioned that we have a Corax.
Yeah, that's another part. I don't have a control how the
Yeah. So this is Corax, and Corax is a experimental, absolutely experimental, extremely experimental. It's so experimental that it didn't exist 2 days ago, and it might not exist 2 days from now. It's basically a way of using Voron as the underlying storage for a full-text search engine. There are some interesting challenges involved with that, and we want to look at that. I don't know if we will do anything with that.
Is there any on the open source for testing?
Yeah, we have done that. It's if you look at the blog, you can see that I've done a lot of reading lately and reviews of how Lucene works. Yes, Matt.
It's more on something that is so machine independent that in theory it can be compiled to VCL and run on Xamarin.
There is, you would have to write, so the problem with that is that you would have to look at what API you have there for memory map files. I think that it's there, I'm not sure. And you have to look at what API do you have there to ensure safety. So do I have the kind of API that allow me to do write through to the local system? Then again, if you're on a phone, you don't care. You're not going to do high transaction throughput, and well, presumably you have a battery. Yeah. So generally speaking, to move to Linux, to move to Xamarin on a phone or that or something like that, you would only need to modify 3 classes. So those are the pager classes that we use to do a whole bunch of stuff, and that would be about it. And maybe a new storage environment option, something like that. One thing that I should mention, currently Voron can work on 32 bits, but it's limited to databases of about 500 megabytes. The reason for that is that virtual memory is heavily constrained on 32 bits. So the general recommendation is to always run on 64 bits. Again, if you're running on a phone and you have to run on 32 bits, you're not going to have a database that is over 500 megabytes. That's not a big deal. Okay, guys, if you have any additional questions, feel free to come to me afterward. Thank you very much.